So next we have
Wesley Fraser.
thank you very much for responding to the call.
He's going to tell us about extreme trans-Neptunian objects and the challenges and difficulties of finding them with the classical and large A solar system.
Hi, everyone. A little early. I'm standing in front of you today. Let this be a lesson. Don't miss group meetings, because the only reason why I'm one of the people in front here is because the group got together and decided this project might happen. I wasn't in the meeting, so of course I was one of the ones that had to write the proposal. So classical and large A solar system, A being, of course, semi major axis. Thank you, Sam, for coming up with an acronym that wasn't entirely forced. A lot of familiar names here. Basically, this came out of the Outer Solar System Origins Survey, a familiar name, and a lot of people will have some talks later in the week about this. I've underlined all of the people that are presenting at this meeting. I think Brett said it earlier, CFHT is a pretty special place when it comes to finding living objects in the solar system, and we'll talk about why that is the case, but that's, of course, the reason why I have so many of these talks. Here's an animation I put together of what I call the known outer solar system. By the way, that little red triangle, or the white triangle, that's the New Horizons spacecraft. Shows you why I say it's known, because it's actually been there. Every one of these dots is a real known Kuiper Belt object as of about Christmas this past year. Their orbits are shown for a lot of the what we call the scattered or scattering disk. Gives you an idea of the extent. The gas giants, of course, those dots, the large circles there. The main belt is in red and in purple. These are color-coded by dynamics. And the rings are at 30, 50, and 100 AU to give you a sense of scale. This is what I call the known outer solar system. Just kind of an amazing thing that even, during my PhD, this was still pretty uncharted territory, but we know a heck of a lot about it now. I color-code these by dynamics because, it tells us a lot about the formation of the solar system. Can't give a talk about the Kuiper Belt now without showing pictures like this. Of course, this was the amazing imagery taken from the New Horizons spacecraft, flyby of Pluto on the left, and Arrokoth on the right. 2,000 kilometers across, 50 kilometers across, very different scales. And one of the focuses of class was to try and understand the processes that allow you to go from dust and pebbles and that sort of thing up to objects like Arrokoth, and then finally up to objects like Pluto. I would say, still a pretty poorly understood process, and that's one of the science cases that we're going to focus on. I'm trying to give you as much background as I can here so that the likes of Justine and Sam later in the week don't have to go through all of that, and they can just focus on the science from Classy. To give you a sense of how we think the solar system dynamically evolved at the beginning, this is a simulation. I actually pulled this together of what we think how the early solar system looked. There's a set of gas giants, and around that, a proto-Kuiper Belt. Of course, is only 1,000 points here. It's not reflective of the millions and millions of points or millions of objects that would have already been in the disk. But the odd part here is the 5 gas giants, and this is actually, people believe this is the favored model, believe it or not. And so you can see, everything is nice and stable. There's a little bit of angular momentum transfer between the outer disk and the inner planets, which cause things to move out smoothly. We would call this a smooth migration. And then right about now, note how there's only 4 planets now. Very quickly, there's an interaction between the inner gas giants that causes one of them to get ejected out of the solar system, and a great dispersal of the disk occurs, scattering most of the objects out of the solar system. And the Kuiper Belt is that 0.1 to 1% survivors of the bomb that went off at 10 or 100 million years in the solar system. I show you this as a sense of the context, because the dynamics and orbits that we get from Kuiper Belt, the surveys of the Kuiper Belt, are in fact the main data points that constrain this sort of history. So it gives you a sense of the sort of things we want to do here. Here is those points that I showed you in that animation at the beginning. These are the points in dynamical space. So this is eccentricity, inclination, and semi-major axis for those data points. And you can see there's a lot of structure here. And as I said, it's in fact this structure, the population of objects in these vertical fingers, the mean motion resonances in particular, are one of the strongest pieces of evidence we have that Neptune migrated outwards quite a significant distance. Now moving on to what Classy is really working on, this is one of the main driving points that, sorry, keep quiet. One of the main driving points that led us to writing this observer proposal is the apparent asymmetry in what people term extreme TNOs. I really don't like this term. These are, in fact, yes, they're trans-Neptunian objects because they're further than Neptune, but, so are comets. Anyway, you can see a stark asymmetry in very distant, very eccentric trans-Neptunian objects. And this is the main evidence for Planet 9. Sorry, I should point out the scale here. That ring that you can see barely on the screen there, that's 500 AU. And so this is now what I call mostly uncharted territory. All the surveys that find these things are usually done by taking a few images at a time on a 4-meter class telescope and looking for things that move. And so your typical depths are like 24th magnitude, which is pretty faint, but not really anywhere near as well as we could do. The reason why people are the theory that has been proposed to explain this asymmetry is Planet 9. This is a very contentious idea. I think most of the people on my team don't actually believe in the existence of Planet 9. I personally don't care whether it's there or not. I want to understand, is this asymmetry an observing bias? Because down in this direction is the galactic plane, and up in that direction is winter, right? So it actually kind of fits pretty well with the idea that this might in fact just be a simple or maybe a complex observing bias depending on your viewpoint. And people are yelling at each other a lot about this now. And so this is one of the main science cases around classes. How can we run an observing program for these distant things that can look in all the different directions at once and try to just see, do we count, is there 3 TNOs that way and 3 TNOs that way? Great, okay, everybody shut up. It's not real. The second one is to try and understand, come back to what we were talking about before, how these things themselves grew up, how we got from dust and moved onwards. That picture of the Arakoth I showed at the beginning is a contact binary, 2 objects that have obviously clumped together in a nice soft fashion to preserve their uniqueness like a snowman. Well, in fact, a lot, if not most, if not all, medium-sized Kuiper belt objects are binaries. And so these are a few binaries that I was able to find in Colossus, which is a spin-off of Ossus looking for colors. This was done with Gemini. We have a few systems now that are known to be triple systems, which is pretty amazing. These are nicely stable things on mutual orbits that are much wider than the size of the Earth. Right now, there's a cute little picture of the Earth for scale. Even though these things are only themselves 100 or 200 kilometers across. And the question of how these came about has been a long-standing one, but we think we might understand the idea. This is not it. So hierarchical accretion is, the likes of Weidenschilling and Kenyon and so on. They've been working on this for a long time, which is basically the idea that small things stick together and grow progressively larger and larger and larger. Unfortunately, it doesn't work. You can produce binaries in this way, but you naturally don't produce a lot of the retrograde binaries that we see. You prefer to produce prograde ones, where there are other means of producing binaries that, that work better. Let's put it that way. This is not the only piece of evidence for why hierarchical growth doesn't work, going from Arakoths down at this size to Plutos on that size. But I don't want to step on it too much because I know Justine's going to talk about it a little bit here. And so I want to just show you some context around the idea that we think does work. This is what you all, when you're driving out here, this is what hierarchical accretion does. Obviously, the amount of bugs you pick up is not a huge amount of a delta on the mass of your car. That's actually kind of one of the problems with hierarchical growth. It's really, really slow. It just doesn't work very well to produce a lot of the Plutos and match the low mass of the Kuiper belt and so on and so forth. So forget about that. I apologize now. It's a bit of a vomit cam animation, but bear with me. Imagine in this case, 10,000 particles in a box. Each one of these is something like a half kilometer diameter, if you want to think about it in size. And it's a gravitationally bound clump. And this box itself is in orbit around the sun, which is downwards. And you can see the Keplerian shear that occurs because it's gravitationally bound. Of course, it collapses. On the left, or your left, your right, my left, there you go, is a box that moves around onto keeping track of the largest particle in this collapse animation. And you can see for yourself, well, it's a binary. Actually, this system currently is a triple. It lasts like that for another 20 years or so, shaking and making you feel motion sick, before eventually that middle particle there gets kicked out, and you're left with a nice, beautiful binary that matches the mass and size scales and orbital period and inclination. It does a very good job of matching what we see in the normal Kuiper belt. I would like to point out the top number there that's racing away. The unit is years, not mega years, not thousands of years. This process of collapse happens in less than the time it takes for this cloud to orbit the sun once. About half an orbit, you go from stuff that is measured in meter scale to stuff that is measured in kilometer scale. And it does an extremely good job of matching the binaries that we see in the Kuiper Belt and the size distribution that Justine will be talking about later. And the way you should think about this, it's just really what causes these clouds to exist in the first place is some interaction between the gas and the dust that originally occurred. A lot of people talk about the streaming instability, like a peloton racing down a highway. The biker at the front is the one doing all of the work, and everyone can catch up behind without as much energy. You can actually do a very good job of trapping enough mass in the gravitationally-bound cloud to do it, to allow things to collapse on the timescales I was talking about. It's not the only way to do it, but it's one way. And so these are the sorts of contexts that Class C was built on. So how do we build this? How do we do this? We need a survey that goes really deep. We need a survey that looks in multiple directions. We need a survey that can track objects for orbits, because without the orbits, we can't put them on the AEI plot. We need a survey that ideally has good enough seeing that we can pick out a few of these binaries, though that's not a super high priority. But it gives you an idea of the three major, what I think of the three major items that went down to making Class C in the first place, is as uniform sampling on the ecliptic as we can. We ended up doing 6 pointings or blocks. These are pairs of megacam pointings together, though we've labeled them by the months that they're at opposition, so August, September, January, February, etc. We want a depth greater than 26 because this is a couple of magnitudes deeper than what is typical for finding other surveys that find ETNOs. And we also need orbits. Just plain and simple. Like, we need to track these things, and you need to track these things over multiple years. Our requirement was a 2-year program, though we're getting 3 on some. These set up the entire thing. And so I ended up asking for a couple hundred hours over a 2-year period, though we'll talk about why we're now in our 3rd year. This is the plan. So here is just a top-down of the solar system. The red points here are our blocks, the 5 surviving ones. We lost one due to weather, and it was just so poor that we decided to not bother trying to chase it down and just focus our time elsewhere. And so we have these 5 blocks. You can see we're relatively well spread out. Importantly, we are looking near the galactic plane where there are no ETNOs known to see if that really is the case or not. So to give you a sense, here is the pointing layout compared to the orientation of the solar system itself. And I think this is actually probably the most unique thing of this program compared to any of the other competitors. They're all doing the one-sided thing still, where we're not. We're actually brave enough to try and get, repeated observations in January when the weather sucks. Unfortunately, we've been really lucky, and the weather's been actually some of the best weather we've ever had. So it's been great. I'll very quickly walk you through the observing pattern itself. As I say, these things come in blocks. Here is the rate ascension declination pointing of the two side-by-side pointings that make up the AS block. This is at discovery, so that is to say when objects are at opposition. To get good orbits, we will also be doing pre-covery and recovery. And so the idea is the yellow box is observed something like a month before the ideal discovery date in GRI. So we're going a little bit deeper than our discovery, which is the green boxes, in R. R allows us to calibrate against all other surveys. We take the R band as a triplet, so it can actually just very easily see the objects moving. And then we do recovery again in GRI about a month later. And that 2-month arc, the parallax that you get from that is really useful for constraining orbits. And then finally, we come back a year later, again in GRI, and we do another triplet on where the objects would have propagated to approximately. And so we're going to miss a few this way. I'll show you that in a second. That's inevitable. But the idea is by moving these boxes along something like a nominal main Kuiper Belt orbit, we can do a very good job of tracking where these objects go in a blind way. And by expanding the field, we don't lose most of them in the next year. I should point out here, the ecliptic is the red band, or the red dotted curve up top, and the invariable plane is the blue one. The Kuiper Belt is not actually centered on the invariable. The densest part of the belt is actually shifted off by about a degree, simply due to the fact that Neptune is forcing some inclination on it. And so we had Yukun Huang, one of Brett's former PhD students, figure out the best spot to look for various dynamical purposes, but it also really helps with our discovery rate. So this, it turns out when you look up on Google Images, crane disasters, there's not very many funny ones. This one I thought was kind of cute, though I really don't understand what happened there. But yeah, so class is a 2-year program because, of course, the crane disaster meant that we lost a whole semester. But the dean listened to our pleas and got an extension, and it's worked out very, very well for us. It's been great. So this is what we did in year 3 for 2 of our blocks. We didn't get the year later observations, and so it means we don't have the orbital fidelity that we need for the program. But it also means that the objects have spread out further, makes our life harder. So not only do we have a bigger area to cover to recover all of the objects, we also have to basically rediscover them again because they've moved far enough that they're now confused by other Kuiper belt objects that weren't in the original discovery field. So our year 3 observations was a 6-field layout and observed in triplets. And honestly, when we were asking for this, we thought, this is insane. There's no way that CFHT is going to be able to fit this in the program, especially with unions. Like, unions was ranked higher than us, so we get the priority. But it worked out just beautifully that you guys were able to get your stuff done and then get out of the way, and then the weather held, and miraculous. It worked out very, very well. So there's been a number of things we've faced. So this is a real object and real discovery on the right. We're using shift stack. So this is actually a 3-hour sequence that we take in a given visit. And you shift and stack at the rate of motion of the object. The projector's not doing very well here to show the negative well behind it because, of course, we use image contraction on the night, so you get a little bit of flux loss. Excuse me. That curve, or that streak there is, well, thanks, Starlink. It's been really good. Yeah, thanks, bud. It's one of the issues. It's actually been a real issue for us. We lose objects this way. We lost MA due to weather. The weather's been a pain in the butt, as we saw. Crane failures don't work out very well for us either. But generally, it's been pretty great. It's actually been really stressful how great it is because every freaking morning I have to get up and do so much work for just keeping up. Here's the steps for the pipeline. I'm not going to bore you with the gory details, other than to say that we thank you, Stephen, for Megapipe. That's a great place for us to start. We use the LSST pipeline for image subtraction. I wrote a shift and stack routine. Sorry, just a sec. Excuse me. I wrote a shift and stack routine that allows us to get theta in 26 like we were looking for. We use linear propagation of detections between nights in a semi-blind fashion to look for possible connecting the dots of the same object. And then we use Brett and his big brain to actually fit orbits to them to say, yes, in fact, these dots are real moving objects and these ones over here are spurious crap. We then do a very good job of tracking and linking in a manual, old-fashioned way because we understand how it works. It's been very good for us. And to kind of just prove the points, here is that AS12 fields. These are in the pre-recovery, so these are not discovered on this night. They were discovered a month later, and these are their positions on the pre-recovery night. And look, now where they're supposed to be, right? And the telescope is pointed, and the objects naturally are falling on it, so we're doing pretty well there. There's one object that's moved off to the left. You might wonder what that one's all about. In fact, it is on the edge, just barely, and it's moving a little bit too fast, or a little bit too fast for us on that side. But the reason why we're able to get it is because in the recovery, it is on the frame as well. And so that's one of the requirements for us, is that we get it at discovery a month or minus a month later, and then a year moving forward. We haven't yet reduced the 1-year data because we're taking our time. But this is what these are the AS recoveries a year later. And here are the orbital uncertainties for each one of those objects. You can see a number of objects with high inclinations. They move above and below, and so they fall off the field. Ones on the left move too fast. Ones on the right move too slow. Rosemary Pike at CFA is using Magellan to do a very, very good job of following up as many of these things as we can. Thank you very much. So we're doing some good follow-up there, but overall the program is working. This is probably the last thing I'll talk about here because I'm running out of time. This is a figure I put together to show you where class sits. So on the y-axis is survey area, on the right, or the x-axis is depth of the survey. The size of each one of the circles is the number of scales and the number of objects discovered. So, of course, Rubin dominates. And And how filled the point is a reflection of the quality of the orbits that come out of the program. So Classy is the magenta one that sits here in the middle. And this is the magic of CFHT. We need the orbits. We need the orbits. It's the only thing that actually sets us unique compared to other competitive surveys is the quality of our orbits. Without those, we lose so much of the science. But other surveys, they don't have the ability to do that because they're stuck in classical or a queue that isn't anywhere near as flexible as a CFHT. So this magenta point here would be looking as empty as all of the others without the magic of CFHT. And so I'm going to jump to that one there and say, this is the thing. This is the thing that we cannot lose. Our temporal requirements in this survey are enormous. It's been very, very difficult for us to keep up. It's been much worse for Q to keep up. They have done a miraculous job. And it's because of the flexibility and the reactivity and the fact that the dean actually listens. Like, we say, this is what we need, and you guys make it happen. Please, and we're moving forward with these community surveys, don't lose that flexibility because it is the key thing that sets CFHT unique. Forget about the mirror and the site and the camera. It's the people, and you've been great for us. Thank you very much.
And thanks, Wes, for making us all remember to thank the staff for the excellent job that they do. Questions?
Well, question from my co-PI. This is all rich.
Going back to your JWS, so the survey plot, yeah. Why is JWST tracking so bad? Can you tell me about that?
Because we have a 2-month arc, and James Webb is much, much, much too expensive to ask for follow-up.
Got it.
So in the JWST arcs are actually only 10 days long, but because of the astrometric precision, it's the equivalent of a 2-month ground-based arc. So like 1 year worth of Classy data is gathered in 10 hours, but it's many millions of dollars to do so. Thanks, everyone.
Excellent. What was the total number of TNOs that you found?
Oh, sorry. In AS, we have about 140, which we anticipated closer to 100 per block. So our total count is going to be 700 something.
And asymmetry, or someone else is going to talk about that.
I'll leave the fun stuff to my followers.
Okay. Any question out in Zoom land? Do we know? No. Okay.